All right, guys, so what we're going to be looking at here is the review for all of your applications of integrals test. Just like all the other reviews that we've kind of done in the past, that I will have all of the answers already on the screen. I'll kind of tell you where I got everything, just so if you want to kind of brush through them, you can see all the answers ahead of time. So let's go ahead and get started. On number 1, it says a toy car driven by a miniature Pinky or possibly the Brain slides down a ramp and coasts to a stop after 5 seconds. From time equals 0 to time equals 5, its velocity is modeled by this. Now again, you can see that that's a velocity equation. I want to know how far does it travel on that time interval. Now, what we do is we set up the integral from 0 to 5 of our velocity function, and that tells us how far we are from where we started. So in this, on number 1, I get 10.417, and if you wanted to put units on it, it would be feet, although I'm not going to require you to do that on the test. So just be aware that's your answer for number 1. Number 2, it says, okay, this is 2 and 3. We've got this fuel consumption of a diesel motor is given by this equation right here. So this is the amount of gas that is being consumed. The first question it asks is how many gallons does it consume in a week? Well, because it is in gallons per day, we're going from 0 to 7, so I would just do the integral from 0 to 7 of that, and I get 31.361. That's the amount of gallons that it uses. Then it says at the end of every day, a foreman that works with a diesel motor fills the tank with 7 gallons of gasoline. How much gas is left? Well, this is where we set it up in a much more traditional sense, okay? I've got my initial condition, assuming that there were 6 gallons, so that's my initial condition right there. Then this 49, where that comes from, is that is the integral from 0 to 7 of 7 dt. Or you could think about it, you just pour 7 gallons in every day, so altogether there are 49 gallons. The 31.361, we got that. That's how much fuel was consumed during that time interval. So this is how much gas we had at the end of that week. Okay, number 4, the electrical power consumption at Annie Lyon's house is typically modeled by, and we've got this equation right here, where T is the number of hours after midnight and E is measured in kilowatts. How many kilowatt hours of electrical energy do Andrew and his posse use in a typical day? Well, again, this is our rate right here. That's letting us know at any given time how fast the electricity is being consumed. I want to know how many hours of energy they're using, so I'm doing the integral from 0 to 24 of that, because that's how many hours there are in a day, and I get 14,400 for our answer for number 4. Number 5, we're dropping this football, we're dropping a tennis ball, and we need to find out how far both of them have gone. Now you'll notice in this case when we put our integral in from 0 to 6, because what we're going to do is we're going to have to find out where each of the different balls are, and then we're going to subtract their distances from one from the other. Well, when I do the football one, I get negative 816. What that means is during the first 6 seconds, that is how far the ball has fallen versus where it started. That's why it's a negative number, because the ball has fallen that much. At the same time, I got the tennis ball at 756. So that's 756 feet from where we started or where we dropped it from. The difference between those two numbers is 60, so the correct answer to number 5 is 60. And it would be, like if you wanted to put units on it, it would be 60 feet. Okay? Number 6, okay? So we've got these two things racing. We've got a turtle, we've got a hare, okay? And I want to know when the turtle's lead is the largest. In order to do that, what we have to do is graph both the turtle's velocity and the hare's velocity. And when you do that, you're going to have to change your viewing window so that both graphs show up on there. I think I changed mine from x equals 0 to x equals 5. And then my y values, if I remember correctly, I did something like 0 for my y min to, I think I did like 15 for my y max. I don't remember exactly what it was. You can probably do it smaller than that. And then what we have to do to find out when, and this is the important part, when the turtle's lead is the largest, is we have to find out where those two graphs intersect each other. Once I do that, remember I just press second trace, number 5, then I press enter 3 times on my calculator, and it tells me at time equals 2.06. That is when the turtle's lead is the largest. Once I know that, what I have to do is I have to find the lead of the turtle at that time. The way that we do that is for my turtle, I take my initial condition, because I found that he got a 20-meter head start, and I add the integral from 0 to 2.062. That will tell me how much further he has gone from when he started. until when his lead is going to be the largest. So his distance there is 20.936. So that is the turtle's position at that time. The hare didn't get any sort of head start at all, so he basically, his initial position was 0 plus that. When I do that, I get 0.485. To find out what the lead was, I would just take those two numbers and I would subtract them. That would tell me that I'm at 20 point, let's see, I didn't do this ahead of time, so 20.451 is what the lead of the turtle is at that time. So again, we just find both of their positions and then subtract them, and that will tell us where the difference in their positions, which is what the lead would be. The next thing that we have to do is find out who is winning the race after 9 seconds. In other words, I have to do the same thing I did on number 7. I just need to find out where each of them are at 9 seconds. So I've got the turtle at 26.482. I've got the hare at 18.370. So obviously the hare is caught up quite a bit, but he hasn't caught up all the way yet. So the turtle is still winning the race. And anytime you're asked a question like this one, you can't just say, I think it's the turtle or I think it's the hare. You have to have the numbers to back it up so you can say, without a doubt, that's who's winning the race after 9 seconds. Number 9 finally moves away from story problems, and we just want to find the area that exists between these two curves. So what we do is we say, okay, I know the interval that I'm looking at from -1 to 3. There's one of my functions, and remember, usually it's top function minus bottom function. But if you screw those up, the only thing that's going to happen is you're going to get a negative number instead of a positive number. Anytime you're looking for the area that exists between two curves, you always will get a positive answer. So in this case, the answer that we get on this one is 15.803. We just type that right into our calculator. On number 10, it's a little bit more difficult because we have these two functions. I've got y equals x squared minus 2, which ends up looking like this. And then I've got another one, y equals 1/8 e to the x plus 1, which ends up looking like that if you graph it. So you'll notice we have this enclosed area right here, and that's what we're trying to find. In order to do that, though, because we are going to do the top function minus the bottom function, I can see that, but I need to find out where the two graphs cross each other. So what we do on this is very similar to our tortoise and hare problem, where we actually find out where they cross, and it just so happens that happens twice. As you can see, one of them is at x equals 1, negative 1.442. The other one happens at x equals 2.386. Once I know those two, all I have to do is put my top and my bottom functions in, subtract them, and I find out that that area is 5.742. So that's your answer for number 10. On number 11, we've got this machine that's filling milk cartons, okay? And we've got the different rates in cases per hour recorded at different times. So notice this one says that we need to use trapezoids to determine approximately how many cases there were filled by the machines over the interval. So basically what we have to do is we have to create a trapezoid for every time interval we have. So my first one goes from 8 to 10. That's where that 2 comes from right there. Remember, both of these are base 1 and base 2 in our example. So 120 plus 115, that's just base 1 and base 2. Our formula is 1/2 base 1 plus base 2 times the height. And the height is always how far apart our time values are. Then we do that for 10 and 11, 11 to 12, 12 to 2, 2 to 3, 3 to 5, and 5 to 6. And that's where each of these different numbers come from. And then we just add all of them together. I didn't even take the time to do that. You can leave your answer just like that. And you're all good to go. And that would be your answer as far as your guess for how many milk cartons were filled based on a trapezoidal approximation. Okay. The last one, or no, we got one more after this. This one says the graph indicates the velocity. And basically what we have here is where velocity is measured in miles per hour. Time equals 0. They are 1.2 miles from her house. And I know this is 12 and 13 on the review. So total distance traveled, what that's asking me to do is that is just asking me to find this area and this area right here. And then once we find both of those, so we just notice that we make that area again. We make that area be positive because it wants the total distance traveled. If you remember, the total distance traveled is just the integral from 0 to 9 of the absolute value of the velocity function. All it's doing is making all that area be positive. So we just find whatever that number is. I don't even know what those are when you add them together. But this right here is your quarter circle, and then this right here is your triangle. And all of it's positive because we're finding total distance traveled. Now, number 13 wants to know how far from her house is she when she arrives at the store. And you think about this. This right here is the initial condition, and then all of this right here is the displacement. Notice this time I did subtract off that area, so I have that, and again, I can't remember exactly what you get, but that would be your answer for how far from the house she is when she arrives at the store. The last example is we've got this landfill being filled up with garbage from time equals -5 to time equals 10, and we want to know what that indicates. Okay, so we look at it, we're like, okay, from -1 to 5, and it does want us to find that value. So I find that right there, -5 to 0. When I find that, that is just 1/2 times the base times the height, which is 12.5 is what you get. That just represents how many cubic yards of garbage were dumped on that time interval, because again, that's just what it represents. Number 15 says to indicate all times the amount of trash being dumped in this is the same as the amount being incinerated. In other words, there is no net change when it comes to like how much trash is being added or subtracted. That's just a really fancy way of asking how many times and where does my velocity graph cross the x-axis. Now the last one says indicate when the amount of trash in the landfill is a maximum. Because this is a velocity graph, and it's the only velocity graph that we have in this example, what I'm looking for is where this crosses. Remember, when we find a maximum, we're looking to see where the derivative crosses the x-axis from positive numbers to negative numbers. That only happens one place on this graph at time equals 6. Again, remember, you're looking at a velocity graph, not a position graph or anything like that. This is a velocity graph, so when it's above the x-axis, whatever it is we're talking about is increasing. Whenever it's below the x-axis, that amount is decreasing. Hopefully all of those made sense. If you have any questions about this, please come on in and let me know.